Today, the very first day of Physics 20, we're going to introduce our new unit called Kinematics. We defined physics as a study of matter and energy and the interaction between the two. The very first aspect of matter and energy in the interaction between the two is called kinematics. It's the study of motion, and for the most part, that's what you did in Science 10 was kinematics. We'll just do it a little bit deeper this semester. It's the study of motion without regard to what causes the motion. In other words, we want to look at what's happening, not why it happened. Next unit, called dynamics, we'll take a look at why it's happening. We'll take a look at what causes the motion to happen. In other words, we'll take a look at forces in our next unit. But for now, we just want to look at the motion itself. Before we do, however, we have to distinguish between two terms, a vector and a scalar. Now, you guys have done these before in Science 10. But I've got a better way of helping you remember what the difference between a vector and a scalar is. A number of years ago, it's probably about, I don't know, 10 or 11 years ago. So about 10 or 11 years ago, I'm at the grocery store with my wife. It was no frills. Now it's, sorry, it was extra foods. Now it's no frills. And I don't really enjoy grocery shopping that much. So sometimes I just kind of look at things. Like I watch people and kind of see how odd people are sometimes, or see how, whatever. Sometimes I just read labels. Well, this one day I was reading the labels in the cereal aisle, and then I saw vector cereal. I never had vector cereal before. And I thought, you know what, I'm going to read the label and see how much different it really is than regular cereal, if it's really any different. They market it as this, thing for athletes, but is it really any different? So it's not all that much different, by the way. But what struck me about vector cereal was not the ingredients and how much it's actually, how close it is to other cereals. But what struck me about it is that it's the only cereal that I could find that day at Extra Foods that has on the side of it directions for use. It actually tells you how to use this. Now, for those of you who aren't sure how to eat this, here's what it says. Place vector in a bowl, add milk. My question is, well, then what? What do I do next? It actually gives you the directions for use. Now, what relevance is that for us here today in Physics 20? Well, a scalar, if you remember from Science 10, is a quantity that has only magnitude. The value of it matters, but that's it. A vector has both magnitude and direction. Not directions for use. It's not really a vector when it tells you how to eat cereal, right? Direction is north, south, east, west, up, down, left, right, and so on. If I ever ask you on a quiz to give me an example of a vector, I don't want you to tell me cereal, vector cereal. It's just a way to remember the difference between a vector and a scalar. Scalar has only magnitude. Cornflakes tells you the size of the box, the magnitude. Vector gives you the size of the box, the magnitude, and direction. Okay, so just a way for us to remember the difference between a scalar and a vector. Don't ever forget that now, okay? You can't forget it. We got vector cereal with direction. We got every other cereal, which is scalar cereal, and has no direction. Got it? Good. Okay, we got three terms here that we're going to define and say a couple things about here. The first one is distance. Obviously, if we're going to talk about motion, which is really what this unit is all about, we've got to know what distance means, and position. And another term that you might not be familiar with yet, displacement. Who can tell me, who can give me a reasonable definition, please, for distance? Let's go to the class list here. Yes? That is a perfect definition. Perfect definition. How far something's traveled? How far something travels? Easy, right? How far something's traveled. Now, usually for distance, we use this symbol, D or triangle D. Anybody know what that triangle is? You guys all know this from Science 10, right? What's that triangle, Jace? Delta. What does delta mean? Good. The difference, the change, right? If we're talking about how far something's traveled, then something's changed, right? Where you are has changed. So usually we put that delta in front of it to indicate distance, although sometimes you can just use the symbol D for distance. The units for distance, there's a whole lot of units that we can use. What's one of them? Miles, sure. Kilometers, centimeters, meters. The typical unit, or the standard unit, is the meter. So that's the one that we're usually going to use. Now, sometimes you can use another one, and I'll tell you when you can and when you can't, but usually we're going to use meters. Now, is distance going to be a vector or a scalar? How far something's traveled? The distance between Calgary and Edmonton is about 300 kilometers. Does it matter what the direction is? No. So it's going to be a what? Good. Distance is a scalar. What your odometer reads in your car is distance. How far you've traveled. It doesn't pay any attention to which way you've gone. I can drive to Edmonton 300 kilometers and then back again, and my odometer says 600 kilometers. It doesn't care that I went north and then south. It doesn't care about direction. Distance just is magnitude only. What's a position? A physics position, not a social position, like a position paper. What's a position? Although it's kind of the same in a way. Socially, you talk about a position paper, it's like it's where you stand on something, right? If you have position, it's where you stand on something. Physics, we say position is, yeah, where something is, where you're standing, where something is. Now, the symbol for position is a D, not a delta D, because it's not, nothing's changed here. You're right here, or you're right there, or you're over there. You're not moving from there to there to there. You're in one place or another. So there's no delta in front of it. There's no change in front of it. The units for position, are going to be meters. And the position is going to be a vector. Where are you? Well, the direction matters. You go to your junior high dance, and the guys are all standing on this side of the room, and the girls are all standing on this side of the room, and sorry, what's your name again? Aiden. Okay. Aiden's with all his buddies at the dance, and he sees this girl on the other side of the room, and he says, geez, I'd kind of like to dance with her. I think she's kind of cute, and I'd like to dance with her. So he walks over, and he asks her to dance, and she says, oh, Aiden, I thought you'd never ask. I was looking at you the whole time. I was going to come and ask you to dance with me. So Aiden's all happy. They dance a few more songs, and the night's over. Aiden says, you know what? He says, I had a good time tonight. I think I'd like to ask you out, on a date sometime, besides, say Saturday night or whatever. She says, Aiden, that'd be great. I'd love to do that. So Aiden says, perfect, let's go to a movie. And she says, perfect. I've been waiting to see this one movie for weeks. And Aiden says, well, I'll pick you up at 7. And he says, where do you live? And she says, I live 20 kilometers from Dairy Queen. Aiden says, perfect, 7 o'clock it is. So then he goes home and realizes, wait a second, what's her position? Where does she actually live? Where is she? at a particular moment in time? Well, she's 20 kilometers from Dairy Queen. That doesn't help him. Where does she live? He needs a direction. So he phones her up and says, you know, Casti, I want to go to this movie with you, but I'm not sure if you realize it or not. You gave me a scalar. I need a vector so that I know exactly where you live. I know your exact position with the direction. Casti says, oh, I live 4 kilometers kind of northeast of Dairy Queen. And Aidan says, perfect, then I'll meet you at 7. Okay, so sometimes direction matters, and sometimes it doesn't. When we're driving to Edmonton and back, on the odometer, the direction doesn't matter. But when Aidan's going to pick up somebody for a date on Saturday night to go to a movie, the direction matters. Position is a vector. Direction matters. Now, because it's a vector, we need to actually change our symbol a little bit. Scalars look something like this. Vectors always have this little half arrow over it. Have you seen that before in Science 10? Have you seen that little half arrow? Yes or no? Yes? It just means that it's a vector. It just reminds us that direction is important. It just reminds Aidan that he needs to not only ask how far from Dairy Queen somebody lives, he needs to ask what direction it is so they can know where to pick her up. Displacement is defined as our change in position. That's it. Now, who can give me the symbol for displacement? You got to think about this a little bit, but you can do it. Even if you've never seen it before, you can give me the answer to this. If position is d with an arrow over it, then what's displacement going to be? Our change in position. What's the symbol for change? Delta. Good. What's the symbol for position? It's what? Yeah, well, not a triangle with an arrow, but you're close. Delta, triangle, right? Yes. And there's going to be an arrow there because it's going to be a vector. But what's position symbol? D. Excellent. There you go. Good. Delta D with an arrow over it. It's change in position. Delta D, the symbol delta D. The units are going to be meters again, although sometimes we use other units, but these are the standard ones. Vector or scalar? Fraser, vector or scalar? Yeah. You know it's a vector for 2 reasons, right? 1, because it's change in position, and position is a vector. And 2, because you look at the symbol and it says delta D with the arrow over it. Whenever you see the arrow, you know it's a vector, because that's the only time we put the arrow over top of it. Now, these things all kind of sound alike. They're similar definitions, but a little bit different. Real similar symbols, same units. Sometimes direction matters, we said. Sometimes it doesn't matter. I'm going to give you a couple of examples now to distinguish, really concrete examples to distinguish between the 3 of these things. Okay? Standing at the front of the room. Okay, I'm going to want my position right now, where I am, we're going to say is 0 meters right now. Okay? So this is the start. This is the starting line on the track outside or whatever. I'm going to walk 5 meters this way. This is north, by the way. So I'm going to walk 5 meters to the north. And then I'm going to walk 2 more meters to the north. What's the distance that I traveled in that first section? I walked 5 meters, then I walked 2 meters. What was my distance that I traveled in the first section? 5 meters, right? What was the distance that I traveled in the second one? 2 meters, right? What was the distance that I traveled overall? 7 meters. Good. Easy, right? What was my displacement? Well, in the first section, my displacement was 5 meters to the north. Not just 5 meters. That was distance. My displacement is 5 meters to the north. What's my displacement in the second section? 2 meters to the north. What's my displacement overall? 7 meters to the north, right? What if we change this around a little bit and say we walked 5 meters to the north, and then we turn around and walk 2 meters the other way. What's my distance traveled? What's my overall distance traveled? Still 7 meters, right? If I had an odometer on me, then it would read 7 meters. You drive your car to Edmonton and then back, it reads 600 kilometers. Doesn't matter what direction you went. So it's still 7 meters. What's my displacement overall, though? Yeah, good, excellent. It's 3 meters. I walked 5, and then I walked 2 backwards. I traveled 7 meters, but my change in position from start to finish was only 3 meters. Does that make sense? So distance and displacement are sometimes the same values, but sometimes there's different values. Here's a rule of thumb. If you don't change direction, distance and displacement will always be the same value. If you do change direction, they'll always be different. Got it? Yeah, if I'm walking to the north and then I keep walking to the north again, distance and displacement will be the same value. If I walk to the north and then to the south, distance and displacement will be 2 different values. You run around the track outside. What's the distance around the track? Anybody know that? Who does track here? Yeah? Yeah, it's 400 meters. The inside lane is 400 meters. Good. So your distance traveled is 400 meters. If you run around the track once, that is, right? What's your displacement if you run around the track once? What's your displacement? What's your change in position? 0. Good. Why is it 0? Yeah. What's your change in position? If I'm here, and then I run around the track and I end up here, what's my position change by? Nothing, right? Why aren't they the same value? Because I changed direction as I went around the track. Okay, so distance and displacement, similar, and always, in fact, the same if I don't change direction. But if I change direction, they become different values. Good? All right, let's do a quick little example that actually appears in your textbook. I know you don't have that yet, but you can see it up on the board here. It says, and this is on page 9 of your textbook, it says a traveler initially standing 1.5 meters to the right of an Inukshuk moves so that she's 3.5 meters to the left of the Inukshuk. So this is her initial position. We'll call this DI, initial position. We'll call this DF, her final position. We want to find her displacement using directions and using her plus minus signs. Who can tell me what her distance traveled is, first of all? That's not asked there, I know, but who can tell me how far she's traveled, what her distance is? I'll give you a hint. If you think you know the answer, you probably do. It's not very hard. What's her distance traveled? Really? 5 meters, good. What's her displacement? Not without using any kind of plus and minus. It's just by looking at it and looking at the direction. What's her displacement? Did she change direction? She stood here, right? And then she went over here. Did she change direction? No, so her displacement will be the same as the distance, right? Except that there'll be a direction with it. So it's going to be 5 meters to the 5 meters to the left, right? How do we figure that out using algebra, using plus and minus signs? Let's say that DI is plus 1.5 meters, because we'll define right as positive. Let's say that DF is negative 3.5 meters, because it's to the left, and we'll define left as negative. Delta D, the change in position of the displacement, will be DF minus DI, which is negative 3.5 minus 1.5. What do we get? Negative 5. What's the negative mean? What did we say the negative meant up here? Yes. Okay, if right is positive, then left is negative, and that means to the left. So in this question, there's more than one way to do it, right? We can look at it and say, okay, we moved 1.5 to the left, 3.5 to the left, it was 5 to the left. Or we can look at the signs. Negative 3.5, which is my final position where I ended up, minus 1.5, my initial position, gives me negative 5. Good? Is that hard? It's not that bad, is it? Oddly enough, the first question that I gave in Physics 30 last class, it's actually a tiny bit easier. So Physics 30 starts out a tiny bit easier than Physics 20. It doesn't end up that way, but it kind of starts out that way. I'm going to ask you right now, just at your desks in your notes, just to take a look at these 3 questions, please, on page 9. You don't need to rewrite the questions. Okay, there's no need of that. But please do just write down in your notes, practice problems, or PP, page 9, just so that you know where to find those questions when you want to go back and review for a quiz or a test. Okay, we'll give you a few minutes to work on those here right now, and we'll see what you can do with them. Don't be afraid to put up your hand or stop me as I'm walking by and ask some questions. All right, let's take a look at question number 3 here. If there's any other questions, just ask me, okay? I just want to, not that you necessarily struggled a whole lot with number 3 and getting the answer. I just want to go through it just real quickly so that we can see exactly how we get the answer, just so that, again, we're not just getting an answer. We want to know why we're getting an answer. It says, while building a wall, a bricklayer sweeps the cement back and forth. If she swings her hand back and forth a distance of 1.7 meters 4 times, calculate the distance and displacement her hand travels during that time. Here's the thing, okay? We know that this bricklayer is going 1.7 meters to the right, and then 1.7 meters to the left, and then 1.7 meters to the right, and then 1.7 meters to the left. We have 4 different distances here. We have, we'll call it distance 1, which is 1.7 meters. Distance 2, which is 1.7 meters. Distance 3, which is also 1.7. And distance 4, which is 1.7 meters. If we want to find the total distance, it's kind of intuitive, right? What do? You add them up. Okay, if we've got 5 people over here and 6 people over here, and you want to find the total number of people, let's add those people up. We get 11 people. Okay, if we move 1.7 meters, 1.7 meters, 1.7 meters, 1.7 meters, and we want to find out the total distance, then we simply add those up, and we end up getting 6.80 meters. D1 plus D2 plus D3 plus D4. Done. The displacement we defined as the change in position. dF minus di. But we don't know what the final position is or what the initial position is, so we can't subtract anything here. You know, and in another example, maybe the first example that I gave you when I was walking towards the back of the room, my initial position was 0. My final position was 3 meters. My change in position would be 3 minus 0 is 3. But we don't know what our initial or final position is here. So there's another way to find the displacement, and that's by adding individual displacements. If you have 2 different positions, in other words, where you are at 2 different spots in time, then we're going to subtract them. If we have different displacements, in other words, how far something's traveled, then we're going to add them up. Displacement 1, we'll say, is 1.7 meters. What would displacement 2 be? 1.7? No, let's not make it 1.7. Let's make it, what am I looking for here? Somebody knows this. I'm just afraid to say it. Negative. Good. Because it's the other way, right? Right, left. We don't know. We don't know which way is right and left, but we know that if the first way that this bricklayer moved the cement was positive, then the second way has got to be the opposite way, whatever way that is, negative. D4 will also be negative. Now notice we're just changing that now when we're talking about displacements. When we're talking about distances, we left them all positive because direction doesn't matter. D1 plus D2 plus D3 plus B4. 1.7 plus neg 1.7 plus 1.7 plus neg 1.7 gives me, what is it? 0. So that's why the displacement is 0 and the distance is 6.8. Now, some of you may have just looked at it and said, I don't need to add those up. I know that she starts where she or she finishes where she started. Therefore, the change in position will be 0, and therefore the displacement will be 0. That's fine. Okay, that's fine. But mathematically, this is why that works. Okay? What I'd like you to do right now is you know what, actually, we're going to hold off on this for a second. I'll give you some time a little bit later to work on these questions. These will be homework, but I'll give you a little bit of time to work on them during scheduled help. Okay? I'd like you to define 3 more terms here right now: time, speed, and velocity. And then we'll do an example, and then that'll be it for the day. Time, you know what? Time, I'm not even going to define that term. Like, try to define time for me. That's the term that really everybody knows what it is. Everybody knows what time is, but nobody can define. Like, look up time in the dictionary. They don't give us, you can't find a good definition for time anywhere. But we all know what it means, so we're not going to bother trying to define it. The symbol for time will be T or delta T. If we're talking about a specific moment in time, it would be T. If we're talking about a time interval, how much time has elapsed, then we'll call it delta T. The units would be hours, minutes, seconds. The standard units would be seconds. Take a look at the symbol there and tell me whether it's a vector or a scalar. Is there an arrow over it? So it's a scalar, right? Times a scalar. Logically, I mean, really, do you put a direction with time? What time is it? Oh, it's 11:21 north. There's no direction with time, right? Time is a scale. How long did it take you to write that test? Oh, it took me an hour to the west. You don't say that. There's no direction associated with time. It's a scalar. Speed. We all know what speed means too, right? It's easier to define than time, thankfully. How fast something's travel. How fast something travels. Its symbol is going to be V. You might think you want to call it an S for speed, but we call it V, a lowercase v. In the units, we can go kilometers per hour, miles per hour, kilometers per second. If you're talking about some kind of spacecraft, usually it's meters per second, though. And if we look at the symbol, it's a scalar. When I drive to Edmonton and back again, my average speed is about 100 kilometers per hour, maybe 110 kilometers per hour. It doesn't matter whether I was going to Edmonton or back, north or south. My speedometer doesn't know which way I'm going. It just knows how fast I'm going. Velocity, on the other hand, we're going to define that as the rate of change of position. In other words, how quickly your position is changing. It's also a V, but it's a V with an arrow over it. Units are meters per second. And it's going to be a vector. Drive to Edmonton, drive back again. What's my average speed? About 110 kilometers per hour. What's my average velocity? About, well, not about, exactly 0. How can it be 0? How can my average velocity be 0 when I went from Okotoks to Edmonton and back again? How can my average velocity be 0? Yep, get it? Sorry? Good. because I didn't change position, right? If we define this as the rate of change of position, and my position didn't change at all, then my average velocity is 0. You think you're fast running around the track? Like you think you can run, 5,000 meters, 25 laps around the track, 20 laps around the track? No. 12 and a half laps around the track. 12 and a half laps around the track really fast. Okay? Take a look at your average velocity. Your average speed during that time might be really good, but your average velocity during that time is 0 because your displacement is 0. I'm going to give you an equation here for speed. It's going to be distance over time. The equation for velocity is going to look almost the same, but we're going to make it displacement over time. I moved from the East Coast to Alberta 18 years ago by myself. I was 23 years old, not much older than you guys are right now. I got in the car. I stuffed it to the roof with my stuff. And I had a map in my hand, and I drove out. It's a long drive. It's 5,100 kilometers. It's 5 really long days of driving. I remember having never been east of Toronto, having never been west of Toronto before. Once I got past Toronto, it was completely new. It was all new to me. And I remember getting to Winnipeg on my 4th day. And I stayed in Winnipeg, and then on my 5th day, I got up and I started driving, and I thought, maybe I can hit Calgary today. I remember getting past Regina, just on this side of Regina, and I remember seeing a sign that said Calgary, like how far Calgary was. Saw it off in the distance, and I got excited because in the East Coast, like when you see a sign like that, you're 30 kilometers from somewhere. Like everything is so much closer together on the East Coast than it is here. I see this sign, I'm thinking, okay, I'm close to Calgary. But when I get closer to it, I realize I'm not that close. It says Calgary. I don't know if you've ever seen this sign. Just this side of Regina, it says Calgary, 750 kilometers. It's a little depressing when off in the distance you think, okay, I'm getting close, I'm getting close, I'm getting close, and then you realize I'm 750 kilometers away. Even if you don't know a lot about physics, even if you don't know any equations, you will, when you see that sign in the back of your mind, figure out how much time roughly it's going to take you to get there, right? Okay? Just real quickly, before we do any equations, and we won't even do equations here today because we run out of time here. How long is it going to take you to go from Regina to Calgary if it's 750 kilometers away, roughly? Somebody have an answer for that? Yeah, a little over 7 hours, right? How do you know that? Because at some level, you just use the equation in your head, v equals d over t, solve for t. That make sense? That's what we're going to do formally tomorrow, is use that equation to solve for t. Sometimes when we get a question that's a little bit harder than just, 750 kilometers, traveling 100 kilometers per hour, how long is it going to take us? Okay? We'll finish this one up tomorrow. That's it for today. Your homework for tonight, or your scheduled help work for tonight, are these questions that you see on page 10 of our book here.